to my channel. In this new series of learning, we're going to be looking at computer science research. I want to use the knowledge that I've learned over the years as a computer science researcher to be able to contribute to the community and help upcoming PhD, master students, or anyone who is interested in doing a research in computer science. Well, you all know that there are tons of resources out there as to why you should choose to do a computer science research as either as a master's or as a PhD level. You could get more information on that in various sources online. But the scope of this lecture series, this being the first lecture, is going to be on when you have decided to do a computer science research, how do you proceed? How do you know which problem to solve? How do you know whether you'll be able to solve the problem? How do you know when you are finished solving the problem? Generally speaking, you want to enroll in a university, in a college, where you will have an advisor, and your advisor has a lot of roles to play in your success. Not only your advisor, other faculty in the department could also contribute significantly to your success in your research journey. So first is you get an admission, you meet up the minimum requirement, and you're in a master's or PhD program for a computer research program. Most schools divide your journey into two parts. The first is the breadth requirement, where you take some courses, an algorithm on programming, an operating system, on computer architectures, on database management system, on machine learning, on deep learning, if the school you are in offers those courses. Some schools don't offer that. You may have to uh, substitute the uh, non-available courses in your school with MOOCs, that is the online courses. There are tons of them on the internet that you can use: Coursera, Udacity, Udemy, and on and on and on. So, because it might not be possible for you to be in a school like Stanford or MIT, where they kind of have everything. So, if you want to do a course on computer vision, you may want to check University of Central Florida, their Computer Research Foundation. They are very good in computer research in vision. They even have a master's in computer vision. For natural language processing, these are research areas that you could possibly work on. You may want to check Stanford has courses on that. The only challenge with that is you go to the Stanford YouTube online, you search for this. You might be able to see all the lecture series from day one to the last day. But the challenge is you may not be able to do the assignment, the project, and also get feedback as well as the exams. Which I would say that is really where the meat of the learning takes place. At least 80% of the learning really takes place through the project, the weekly assignment, and also the exams, because you get feedback on your progress and you are kept on track with your work. You get to also work with other teams, and you have TA assigned to you to be able to monitor and give you feedback on your grades. But that's not to discourage you. If you feel you're not fortunate to be in such a school, you can still create an alternative for yourself. First, the best you can do is to watch all the online courses on that particular area, and you may want to go to uh, the online courses like Coursera, Udacity, Udemy, and the likes, and take similar courses. Some of them are free, some of them are paid, some of them are financial aid, where you can get some feedback. Or at worst, you may have to self motivate yourself to make sure that you do some of the assignment. So the research areas are enormous. You could be working in a research area of computer vision, natural language processing, reinforcement learning, high performance computing, and on and on and on, speech recognition. My recommendation will be, and this is not one cap fit all, this is just my own recommendation. You might find something else better for you. Is that you work with whatever your advisor has project funding on. That will be my recommendation on that. That's what I consider the easiest way of choosing a research area to work on without you thinking about, is it viable, is it something interesting, is it something challenging. If your advisor has a funding from NSF, National Science Foundation, or NIH, National Institute of Health, or from NASA, or from all these project funding organization, you can be sure that those projects have gone through a lot of meetings, deliberations. They've looked at it, a lot of experts have looked at it, formulated it, and see that it's something interesting, challenging, viable, and a good application, and it's a problem that have not been solved. So a lot of questions will have been answered for you, so you don't need to start asking yourself, is there an interesting question? Will you be able to publish on it? Because if it's a problem that has been solved, they won't even give it any funding. So that's the approach I would say that you should go about selecting a research area. One way, just work on, at least for the start, for the first one or two projects, start with that. So if you start with that, you are guaranteed you are in a safe place, safe area. Then how do you build more knowledge once you have chosen that research area? Conferences. Conferences are indistinguishable. You have to attend the conferences. Now, thanks, most conferences are now running online, so you could, with a little fund, with support from your advisor, you should be able to attend those conferences online. What do you do when you get to the conference? You are just doing what you call exploration. Initially, you don't even know what is what. You just go there and just keep jumping from one session to another. Keep listening. You listen to some talk, you see, oh, this doesn't make sense to you. You listen to some, it looks like it makes sense. You just keep listening. Just take your time. Keep doing that from one conference to another. Be consistent. So conferences like NORIPS, their top tier conference, ICML, ICLR, CVPR, ACL, all these conferences, irrespective of even if you have chosen a research area, say in computer vision, just from start go to these conferences and just get to see how they do things and just listen. You can't contribute initially. Just listen, you see, okay, what people are working on, what they are publishing on. So, excuse me. Now, your knowledge will begin to converge after some time of going to conference. You begin to see that there are similar projects that are being taken as maybe workshop or tutorials in conferences or papers that people are published on posters that are similar to what your advisor has funding on. Then you begin to see that, oh, this is a current area of research that people are working on. That means it's still actively being researched. So there's an unsolved problem there. Okay. So I'll be rounding up now. Will I be able to solve a research problem? Well, that's dependent on you. We don't know. Nobody knows. The advisor does not know. No one knows whether you'll be able to solve an open research problem, whether you'll be able to contribute. So it's a journey that we don't know whether you're going to arrive at the destination. However, there are signals. There are signals that tells the university, the admission committee, as to your viability of success. That's why they have requirements, admission requirements. There's some examination you take. Your performance on those exams will tell you're a good candidate. And even after you have been admitted, you take courses in the university. Those courses, algorithm courses you're taking, your performance and your understanding of those courses and those projects and those exams give signals as to whether you'll be able to adapt the knowledge you have learned into a novel research area. For instance, let me take an algorithm like quick sort, merge sort, selection sort. Yeah, all these sorting algorithm. If you find it difficult to understand this sorting algorithm, there might be an indication that you may be weak in being able to formulate a step-by-step solution to a problem. But if you find yourself being able to understand how those algorithm works and you're able to uh, close your notes and put them down in codes and explain them, then it means that you have the kind of brain like the people that originally created those algorithms. You have the capacity to understand the problem that the algorithm is solving and capacity to understand the solution that the algorithm is providing. So if you do, then we can be sure that you will have capacity to be able to solve an unsolved problem. That's just the best case of one. So as you proceed, we have kind of answered that. You proceed in an iterative fashion. There's no linear way of going about it. There could be even many more ways that I don't even know. So it's an iterative fashion. Initially, you keep moving from what your advisor is doing, checking conferences, checking what other students in the lab in your group are doing, small senior students, those who are finishing, those who are graduating. You start watching what they have done or what they are doing. Then begins to give you signals as to what kind of things you two should be expect. At least something similar, may not be exactly. Then there are presentations, seminar presentations in your group, in your department. What other PhD students are doing, you listen to them. Then if it begins to make sense to you, if one or two begins to make sense to you, then you may want to explore that a little more. In rounding up for this session, I would strongly advise that you start solving a problem, you start working on a problem that you understand the problem. I'm not saying that you understand the solution. The first step is, do you understand the problem? If you sit down in a lecture or in a conference or in a tutorial or workshop, and in the first 15 minutes you are blank out, then that's not an immediate area of research that you should embark on, because you don't even understand the problem. And if you don't understand the problem, there's no way you can understand the existing solutions, and there's no way you can contribute new approach to solve a meaningful aspect of the problem. All right, thank you all for listening, and see you in the next one.